Okay, we're in 15.3 now, double integrals in polar coordinates. So just a quick recap, 15.1 and 15.2 were all about dealing with double integrals. The only difference between the two is that in 15.1, the region that we integrated over was always a rectangle. That's the easiest case. 15.2, we talked about more general regions, type 1 and type 2 regions, where your region is bounded by either a function of x or a function of y. In 15.3, the regions that we're looking at in general can be thought of as type 1 and type 2 regions, or can be pieced together by type 1 and type 2 regions, but using the approach in 15.2, for the examples we see here, tend to create more work than we need to do. So we're going to find that if we come up with a way of converting everything over to polar coordinates, certain integrals will be much easier to evaluate that way. But we need to make sure that we know what we're doing if we're converting things to polar coordinates. So to kind of illustrate what kind of regions we want to convert to polar for the purpose of doing double integrals, regions like circles, or this is half of what's called an annulus, or a ring, a two-dimensional ring shape. These sorts of things are easily described using polar coordinates. The things that kind of are circular, or we've talked about graphs of polar functions back in calculus 2 and far back as trigonometry, things like cardioids, limesons, lemniscates, all those fun things. Those types of regions are better described using polar coordinates. So as we've been doing throughout section 15.2 and 15.1, when we talk about a region that we want to integrate over, we first figure out what that region looks like as a set. And where this section, where the sets are going to differ here, is that instead of having sets where the points are expressed in terms of x, y, the points are going to be in polar form, r theta. So for example, if I have this circle right here, x squared plus y squared equals 1, it's a circle of radius 1 centered at the origin. The points in this circle all are within 1 unit of the pole, or the origin. So r, for any point in this circle in polar coordinates, r is always going to be between 0 and 1, within 0 to 1 units away from the pole. Theta, the angle that that point makes, if I connect it with a line joining that point to the pole, the angle that makes with the positive x-axis, or what we call the polar axis, is going to take on any value between 0 and 2 pi. You can see that if I choose any point in this circle, the angle is going to be somewhere between 0 and 2 pi. So this describes the set of points, but in polar coordinates for this particular region. In this region here, which I'm calling R, it's the region bounded by two semicircles. So the smaller semicircle, x squared plus y squared equals 1. This one, x squared plus y squared equals 4. We have, this is a semicircle of radius 1, semicircle of radius 2. So how do you describe this as a set of points, this entire region, thinking of it in terms of a set? Well, again, the set of points look like r theta, polar coordinates. And this time, there are no points that are close to the pole. All of the points are within 1 to 2 units from the pole. So r is between 1 and 2. Theta this time doesn't go from 0 to 2 pi, because we don't see points going into the third or fourth quadrant here. All the points lie within the first and second quadrant. That would mean that the angle that each one creates with the polar axis, the positive x-axis, is somewhere between 0 and pi. So these two intervals, this interval for r and this interval for theta, describe the set of points in this region. Okay. Now, because we're going to be converting back and forth between rectangular coordinates, that's x and y, and polar coordinates, that's r and theta, we need to kind of recall some of our conversion formulas. So we have r squared equals x squared plus y squared, x equals r cosine theta, y equals r sine theta. You derive these in trigonometry. You probably rederive them in calculus when, calculus 2, when we start using polar coordinates again. So I'm not going to derive those here. You should be pretty familiar with those. So how then do we handle the problem of integrating, doing a double integral of a function that's expressed in terms of polar coordinates? Well, the starting point for us is going to be rectangles, except not a normal rectangle. It's going to be something that we call a polar rectangle. If you go back to 15.1, where we only stuck to rectangular regions, those rectangular regions came from an interval on our x-axis and an interval on our y-axis. The interval on our x-axis we normally called AB. For the y-axis, the interval CD. Those two intervals intersected in the form of a rectangle. Okay, but if we're looking at intervals not for x and y, but for r and theta, the rectangle that we get from these types of intervals doesn't look like a normal rectangle. It looks like one of these. This is what we call a polar rectangle. Notice that for any point here, if I let r be some number between a and b, here's a and here's b. So if r is between a and b, it's somewhere between those two arcs of these concentric circles. These would be concentric circles if I completed the whole circle. Theta in this case lies between theta equals alpha and beta. So all of these, if I were to draw a bunch of line segments through here, they would all form an angle somewhere between alpha and beta with that positive x-axis here. So that's what a polar rectangle looks like, which is just what you get when you put an interval on your r and an interval on your theta like this. Okay, so if we think about how we came up with the process for evaluating a double integral in rectangular coordinates, we started with our rectangle, and then each of these intervals, the interval for r and the interval for theta, we broke up into a bunch of equally sized subintervals. In the case of 15.1, it was x and y. We broke those up into a bunch of subintervals. And then what that did to our rectangle is it created a grid of smaller rectangles within that larger rectangle. And then we used those smaller rectangles the same way that we use subintervals with Riemann sums back in Calculus 1, how we define the definite integral. We want to do the same thing here. If I were to take these two intervals for r and theta and break them up into uniformly sized subintervals, I would get something that looks like this. So, for example, if you take your r and break it up into subintervals using the notation like R1, R2, R3, so on and so forth, then you get basically this series of concentric circles, each of which is equally spaced apart from each other. If I take my theta interval, so theta which goes from alpha to beta, and I break that up into a bunch of subintervals denoted with their endpoints denoted by theta 1, theta 2, and so on and so forth, then that corresponds to these different spokes. I like to call these spokes because if I made a big circle here and put a bunch of lines through them, it looks like spokes on a bike wheel or something like that. So you get these different spokes which are uniformly spaced as far as their angle between each other. That creates these this grid of polar rectangles in here. Okay, so now we need to try and create some kind of a Riemann sum out of this. So here's the notation I'm going to be using. Any one of these particular polar rectangles I'm going to call Rij, where I corresponds to Ri, so which subinterval for my r I'm using, and the j corresponds to which subinterval for the theta I'm using. So here's one particular Ri that was selected, this polar rectangle right here. If you remember, when we're talking about Riemann sums, for double integrals, we take those little rectangles that we found in our grid and pick a sample point in there, which is supposed to then be plugged into our function. For convenience, for the calculational convenience that's going to come out of this next step, I'm going to select that to be the midpoint of that polar rectangle for each one of these. That's going to make the formula that we use for double integrals in polar coordinates much easier to derive. So what would that look like? Well, if it's the midpoint, then r for that point is halfway between the r at the bottom and the r at the top here. So I could find that by taking the average of the endpoints of the interval that I'm using for r. That's 1/2 times r I minus 1 plus ri. That's just a mean or an average. Same thing with my thetas. The theta, if I were to take that point and create a line segment joining that point to the pole, and then measure its angle to the x-axis, it's halfway between this angle and that angle, which I can just average those two angles to get that theta. So that's what I'm going to call ri star and theta j star. That would be the coordinates of this point in polar coordinates. All right. In addition to that, this polar rectangle, as we know from 15.1, when I'm trying to come up with the Riemann sum, I know that I'm going to need the area of that rectangle as well. I called that delta A in 15.1. Now, where this differs from the area of the rectangle that we talked about in 15.1 is in 15.1 when we divided our x and y intervals into uniformly sized subintervals, all of those smaller rectangles were the exact same size. So I just called that common area delta A. But you can see from this picture that these rectangles are not necessarily uniformly sized. However, if you kind of think of this as like little almost circular bands, the area of any one of these little polar rectangles within one of these bands are all going to be the same. If I move up to another band, these areas may be different than the areas down here, but each one is equal, or they're all equal to each other within that band, if that makes sense. So any rectangle within this band, because that band corresponds to the ith subinterval for my r, I'm going to call that delta AI. That's going to correspond to the area of any one of these subrectangles. Okay, hopefully that made sense. So down here, I want to come up with a formula for how to calculate delta AI. Now to explain this, actually let me go back to the picture for a second. This little polar rectangle can be thought of as sort of like a little piece of a sector of a circle. Now the area of a sector from trigonometry is 1/2 r squared times theta, which is the angle that subtends that sector. Okay, now if you think about it, if I want the area of just this polar rectangle, I can take the area of this sector where r goes all the way out to the further boundary of this polar rectangle. That's ri in this case. And then I can subtract from that the area of the sector that only goes out to ri minus 1, this lower boundary. If I subtract those two areas, I'm left with this polar rectangle. And that's what's happening right here. Here's the area of the larger sector minus the area of the smaller sector, where notice delta theta corresponds, you can see it in the picture, delta theta is the angle between any two consecutive spokes. So it's the change in theta across each of these little subintervals. That's what would be used here. So if I subtract these two and then do a little algebra on this, notice I can factor out a 1/2 as well as the delta theta. I brought them out to different sides. What's left is ri squared minus ri minus 1 squared. As a difference of squares, I can factor that like this. Now, 1/2 ri plus ri minus 1 appeared up here. That's what ri star was equal to. So I can change that into an ri star. And this, ri minus 1, if you think about what that is, that's the difference between the two endpoints of that polar interval. So this thing I can think of as delta r, the change in r as I go from one endpoint to the other in my subinterval. And again, this is ri star. So the whole thing simplifies down to something pretty nice. Ri star, delta r, delta theta. How then do we use this to come up with a definition for a double integral in polar coordinates? Well, we know that the definition of any type of integral comes from a Riemann sum. So we want the limit as m and n both go to infinity for this double sum, f of xi star, yi star, delta ai. I'm using a delta ai instead of a delta a, again, because we don't know that the area of all of those subrectangles, those polar subrectangles, are going to be the same. Now, I have to make some substitutions because we want to talk about things in terms of polar coordinates, not rectangular. So I'm using those conversion formulas on the previous page with this xi star and this yi star to convert those into these expressions in terms of ri and theta j. Okay, that delta ai on the previous page we said was equal to this expression, ri star delta r delta theta. This looks like a Riemann sum that I can work with. And this thing right here, whoops, is the function that's going to turn into our integrand. Notice it's f of ri star cosine theta j, ri star, I'm actually missing stars on those. There should be stars on those thetas right there. Sine theta j star. And then this ri star out here becomes part of that function, but it gets multiplied to it once this turns into an integral. My delta r and delta theta become a dr and a d theta. And so what we have is this formula for converting a double integral in rectangular coordinates into polar coordinates. Notice because the order of integration has me doing dr first, I use the limits of integration for r here, a and b. D theta has limits alpha and beta. Okay, and so this summarizes how we do that kind of a double integral. On the next video, I'll run you through an example, and I'm going to point out probably over and over again every time I do one of these to not forget about this r right here. That's going to be the common mistake that everybody makes, but we'll do that in the next video.